This meeting is being...
Okay, again, welcome to, if you guys don't hear me well or there's an issue, please let me know, because like I said earlier before the rest of you came in, and the ones who are not live actually are not here, I changed a little bit devices in here, so you see things a little bit not similar to the way they used to be in terms of lighting and in terms of sound. I want to make sure that everything is working fine in terms of that. Okay, so that's the only thing I want to announce about this. Today is chapters, basically the chapters that combine both sound and waves. Typically, these two things are only, basically, they can be put together, yes, because actually sound is a special case of waves, okay? Sound is a wave. So that's why I decided to put them together. As a matter of fact, even the next chapter can be added to them. So a lot of these things can be, there is a crossover. I know those who are sitting in Physics 11, we had a big lab not too long ago on this thing, on waves. And so they might have a little bit of an added advantage versus the people who are not sitting in that class. And but hopefully you guys don't miss much, because we should cover all the entire topic. So there are two key ideas in here, okay? And this is item 1 of the discussion. Vibrations and waves, okay? Two different things. A vibration is an oscillation or an event that happened in a specific location in space. It changes with time, but it doesn't move from point to point to point to point, okay? I'm trying to think of a way of doing it, demoing it in here. I'm trying to build a pendulum in here quickly. Let's see if I can do one. Oh, magnets are no good, okay? I have this thing that I'm gonna use at some point down the road with you guys, which is called the solenoid. I'm gonna attach it to string, and this is a vibration, okay? An oscillation, if you wish. It's localized. In other words, this mass goes back and forth, but it doesn't travel forward, it doesn't travel backward, it doesn't go the whole thing. I mean, it oscillates around an equilibrium. So this is the equilibrium, if I let go of it. If I move it out of its equilibrium, it wants to come back to its equilibrium. But the minute it gets back into its equilibrium, it has kinetic energy, which keeps it going out of its equilibrium. So it wants to go back its equilibrium. So this is an oscillation, or if you wish, a vibration, okay? A wave, on the other hand, is a disturbance. I'm going to create a disturbance in here, or an oscillation, if you want to call it an oscillation. But that is not localized. It moves in space. For example, if I create a disturbance at the end of this string, it's going from this end of the string, and I will feel it on the other end. Of course, you saw the string. The entire string vibrates because of the fact that I created it only in here. I didn't create it everywhere in the string. Yet the whole thing traveled. Another example of a wave is sound, okay? The way the sound works is basically I am putting a pressure on the air surrounding basically my mouth, okay? And that's how we talk, basically. We create a compression and we create a pressure, and that pressure travels in space and goes all the way to where my microphones are. Then, for this special case, since we're sitting on a Zoom session, it's going to basically travel, convert it to an electronic signal, went through the internet, and comes to your device where you're sitting and listening. The device takes that electronic signal basically, and converts it back to you as sound. So it goes through the speakers, and the speakers again exert pressure in the air surrounding your speakers that are coming either from your microphone or from your computer or from your phone. And then they travel in space. They travel surrounding the area completely where you are seated, and then at some point they will reach your ear. And the eardrum will move accordingly, depending on the frequency, how often the sound is going back and forth, and also the intensity, how far it moves back and forth. Your ear now interprets that at different frequencies and different intensities. And that's how, actually, not your ear, your brain, actually. The signal also is transferred from your ear through the nerves to your brain, and your brain gives you a perception of what that sound is. So again, that is the whole thing started with my mouth exerting an oscillation, in this case, around it. It did not travel in space. Okay? So what traveled in this case is the wave. So the first point of discussion, the difference between vibration or oscillation, which are the same thing, and the wave, is that vibration or oscillation are localized in space. They happen only in specific points, okay, in space. The only reason why you saw the pendulum earlier is because there is an electromagnetic wave, light, that traveled and was captured by the camera, and that light was captured by the camera, again converted into an electronic signal, and your monitor or your screen or your phone displayed that back to you. Okay, again, what happened in this case, the wave that took that picture, and that wave is an electromagnetic wave, meaning it's light. So when it hit your eye, again, the eye took the picture of the camera, and it's changing live in time, and projected it on your retina, and the retina had nerves also attached to it that send a signal to your brain, and your brain gave you perception of it. So what traveled in that case, not the actual oscillation, it stayed in its place. What traveled in this situation is actually light, okay? And light traveled all the way from my basically experiment, from my demonstration, right into the camera of where I'm seated. The rest was taken by electronic signals until it got to your screen, that converted that into an image in front of you, and that image again traveled through a wave from your screen down to your eyes. So this is basically the difference between them. Do you guys understand? So this is the issue number one. An oscillation or vibration is not a wave, okay? A wave travels in space. An oscillation does not travel in space, or a vibration does not travel in space. It's localized. So this is item one. So let's get going then with the topic, because these chapters are kind of loaded in terms of a lot of terminology, but I think conceptually should be easy, okay? There are a lot of verbiage that are used, a lot of words used, heavy words. So let me share with you the screen. Where is my stuff in here? PowerPoint. Okay, here it is. So again, vibrations of a pendulum. I already demoed the pendulum already for you guys. I don't know what happened to it. Here, okay. So this is actually a pendulum, okay. So what you have in this case, you have a mass and you have a string of a given length or a rod, and then an equilibrium is like this. So you give it an intensity in here. How far you move it, that is basically the intensity of the oscillation, because it can move from all the way here to back. That is the intensity of this one, or you give it a very small intensity, so it's going to oscillate slightly. Here it's going to oscillate more. So that is, again, how we describe it. How long does it take for it to go up, back, this way, and then come back to its original position? That time is called the period, okay? So this is some of the properties of the vibrations or oscillations. Two key concepts, the amplitude and also the frequency or the period. Period and frequency are related to one another. And again, we're going to talk about waves. Waves, again, it's the same thing, except that it doesn't stay in its place. It moves from point to point to point to point, okay? There are two kinds of fundamental frequencies, fundamental waves, basically, as we discovered from Physics 11 when we did the lab. We have a bunch of types of waves, and probably you got sick of them. But the point being in there, they all could be broken into one or the other, or a combination of transverse and longitudinal waves. So there is transverse wave, like the one I was demoing earlier with the string, that in that case, the oscillation is going up and down in the string, whereas it's moving along the string. So it's going very perpendicular to the string, the motion, and the wave is traveling along the string. So in this case, it's a transverse wave. Whereas in the case of the slinky, for example, which I have in here, okay, the compression, as you can see in here, that I'm going to create, that I have created, is along the slinky itself. So let go of it, that compression will travel along the string. It goes up and down. So this is a case of a longitudinal wave or a compressional wave. It has two names. They call it either longitudinal wave or compressional wave. Any wave that you see out there is either one of them or a combination of the two. For example, the surface water waves is a combination of both, because the water is going up and down in a circular fashion. So at some points it's going along the direction of the wave because it's going back and forth, and sometimes it's going up and down too. So it's going on a circular path. So in that case, actually, they are both. Okay. Examples of this too. For example, I just gave you a couple of examples. Sound turned out to be a compressional wave or a longitudinal wave. Lights turn out to be a transverse wave. Okay. You have an electric field going up and down. You have a magnetic field going left and right. And both of them, they're moving opposite in perpendicular direction to where they are doing their oscillations. So the electric field is oscillating up and down, for example, or left and right, or at an angle. At any rate, the magnetic field is perpendicular to it and is also oscillating. Both of these two are moving together. I know we didn't do electricity yet for physics 10, so we don't know what an electric field means really and what magnetic field really means. But the point being, those are the two essential things. And once the electric field from light hits your eye, it moves the electrons in hair-like structures in your retina. And those electrons, once they move, they create currents, and those currents are translated to your brain. And the brain tells you exactly what color you're looking at, okay? It combines the different colors and shades of colors to give you an impression of the object and how that object looks like. So this is, again, the stuff that we again, it's a combination of the two, either transverse or longitudinal. Waves have a peculiar thing they do together. Nothing else does it in nature except waves, and that is they interfere with one another, okay? The phenomenon of interference is a signature of a wave. If you see two things interfering with one another, you know you're dealing with a wave. So how do I tell I'm dealing with a wave or not a wave? Try to see if they interfere. If they do, then in this case, you have a wave. Okay, you're dealing with waves. Okay. Then we're going to discuss standing waves. Standing waves are basically kind of interference, if you wish. Okay. You have waves, they travel to the right or the left, first of all. For example, on my string, on this string, I could have created a disturbance. I did create disturbance this way, or I could have created it on the other side. It's the same thing. One wave is traveling to my left. I don't know how you see it on your screen. And the other way is traveling to my right, okay? So one of them, I'm going to call it a right traveling wave, and the other one, I'm going to call it a left traveling wave. Now, if these two waves happen to have the same frequency and also the same amplitude, and they hit one another, and if they continue to basically oscillate, they become standing. They don't change. There will be actually, there will be points where they are going to form. They don't move at all. They're called nodes. And there will be points where they are going to be moving at a maximum intensity. They are going to be called antinodes. Okay, we're going to learn the rules of nodes and antinodes in this case in terms of waves. And then we're going to talk about a very important concept, the Doppler effect. Okay, again, the Doppler effect is common to both all waves. Okay, they do Doppler effect. Bow waves, they happen on surfaces, and shock waves for the case of supersonic, basically in the case of sound, or when the wave is traveling with a speed that is, or the source is traveling with at least the speed of the wave, okay? Typically, this is for sound, or the shock wave is really something that we talk about it in terms of sound. Again, sound, like I said, is a wave. The origins of sound, basically, and the one of the phenomenon also that waves do, all of them, and this was part of the lab too for physics 11, is the reflection and refraction. When wave hits a medium that it cannot transmit through it, is either, of course, absorbed or re-emitted back, okay? So if it comes to a reflection, there is a law that governs the reflection, and namely that the angle of incidence is equal to the angle of reflection, okay? Now, if the wave can be transmitted through the medium to a different medium, in this case, in this case is going to be transmitted in such a way that the angle of reflection, I mean, say the angle of refraction, where it's refracted to, and the angle of incidence are related to one another through something called the index of refraction when we talk about light, okay? And the same thing is true actually for sound too, okay? But the index is, in this case, is how fast the sound travels. For example, if I'm talking about sound in the air versus sound in water, they travel with different speeds. Or sound on train tracks, for example, they travel on solid iron, for example, travel faster than that of the air. Okay. Energy of waves in general is proportional to the square of the amplitude. So all waves have that. And again, that was part of the thing in the lab too for physics 11. Okay. Force vibrations, there are so many kinds of oscillations basically that you can have, and also waves too exhibit the same phenomenon, and this leads to the concept of resonance. Okay, any object has its own natural frequency. The natural frequency for this one is related to the length of this material plus where it's located on Earth, for example. Okay? If it's on Earth, it's g. Okay, so this is a natural frequency. If I change the length, the natural frequency changes. So every object has its own natural frequency. Basically, if I move it out of its equilibrium, how fast is it going to go back and forth in 1 second, basically. That is what the frequency is. Now, if I have, in addition to the fact that it's going on its own, I'm giving it every time another boost. Now, if my frequency, the one that I'm giving, this is the forced motion, basically. This is not a natural motion. This is enforced. But if I keep on hitting it every time it comes back, this is going to be now boosted, basically, or forced oscillation, excited. Okay, there is an excitation in this case that keeps on basically adding to it. If the natural frequency is equal to the forced frequency, in this case, I have resonance. Okay, they're equal to one another, so I have resonance. And the amplitude will be large. The amplitude of oscillations will be huge. Okay, so that is basically something that sometimes is not good to have. So you want to minimize its effects. For example, you don't want the building to be in resonance with the next time the wind blows, because then the building starts to shake violently and it's going to break apart. Okay. You don't want the singer, when she starts singing with her own frequency, and that forces the cup, basically, or the glass cup, to start to oscillate with its own natural frequency. If these two are very close from one another, or equal to one another, the glass will break, will shatter. Okay. Those are sometimes when probably you don't want these things, but sometimes the other way around. You really want resonance to happen. When you tune in on your dial, for example, for an old radio or TV stations, what you're actually doing, and even actually with the one when you change frequencies, what you're actually doing, you're bringing the natural frequency of your device to match that of the broadcasting station. You would want them to be equal, so that the signal received by the device in this case is at its best. It's amplified later on, and you will hear music, or you watch something or something like that. So in some case, in terms of telecommunications, it's important to be in resonance to capture that signal. Okay, so it's used extensively, resonance, a lot. It's used actually in medicine too, with to force, for example, specific elements to appear in an image. In magnetic resonance, for example, imaging, it's used a lot everywhere, almost. Resonance is used a lot. For example, you would want a compound to be excited, and based on whether or not the excitation is corresponds to the natural frequency of the object, if that object is in there, it's going to resonate, and you will see it there. Okay, so it's used also in analysis extensively. So this is a very important thing that is used. Yes, Amanda? You have your microphone on. Do you want to say something?
Oh, sorry, you were cutting out there. Sorry about that.
Okay. Is the sound coming correctly, or is it not good? I would hate to be right. Okay. Okay. So, and then we're going to talk about interference again. We basically said that that's a signature of waves, because sound is a wave actually. And then we're going to talk about beats. Okay, I have a tuning fork in here. This has specific frequency. Okay, this is the C note. Okay, this is 512 hertz. Okay, if I'm going to first of all get it going, I have to hit it with something. Okay, did you hear it, guys, or not? There is a, it's kind of low intensity. Not the first hit, okay, but there is the frequency that comes. It's still there. At least I can do it. Okay. Maybe because the this thing is supposed to have noise cancellation, so I think it's noise, so it's canceling it for you guys. Did you hear it? Okay, very good. So that is basically the note that is used. So what I have in this case, I have a tuning. Basically, we use it actually for experiments in the lab, or we put it in amplifiers with boxes. I mean, not basically wooden boxes and things like that. But the point being in here is that for piano tuning, for example, if a person is working in that industry and wants to tune the piano, and he knows exactly that there is the note C on the instrument, okay? Hit the note C, hit this one, and both of them. If the piano is working perfectly, you should hear nothing but as if it's only one sound. Both of them will count as exactly one sound. Okay, you don't see a difference between them, and you will hear only one of them, which is the same, either this or that. Basically, that's it. That's the end of it. If the piano is out of tune, namely that it needs either a tension increased or lowered. Okay, so one of the things you need to do, you will hear there is this frequency, this main sound that is produced both with the piano and the tuning fork, but you will hear a hum that comes at the end. Okay, so what you do in this case, you increase the tension in the chords of the string for that specific note, or you lower it. You increase it and you hear the hum. Is it going away, or is it getting closer and closer? Okay, if it's getting closer and closer, that means you're on the wrong way completely. So if you were increasing the tension, you actually needed to lower it until that completely disappears. So that phenomenon is called beats. When two frequencies are close from one another, they will create another frequency, and that frequency is actually the difference between the two frequencies. Okay, it's used a lot extensively for tuning devices, for trying to determine specific frequencies and measurements and things like this. So it's used a lot. This beats. Okay. The mathematics is outstanding, but we're not going to do a lot of mathematics with waves, okay, except that this is the ones that we're going to do with. All of these types of waves that I talked about, they're so-called linear waves, okay? If I have one wave and I add to it another wave, I will get another wave that is the sum of the two waves, period, end of the story, okay? There is another type of waves that are, they can be violent and they can be chaotic. And those are basically when you have a lot of oscillations that can lead to chaos. Case in point, for example, turbulence, or what you may call them, those tornadoes and things like that, or solitary waves like tsunami, for example, which are non-linear waves. Okay, those are they call them solitons. So waves is a huge topic. Okay. And we are surrounded with them. As a matter of fact, we're bathing right now in a tremendous amount of electromagnetic waves, okay? Sound everywhere, okay? So waves are everywhere, and this is one of the phenomena that we study in here. This is the entire chapter, guys. 2 chapters, we covered them. Any questions? Or should we go in a little bit more details? Okay, now we have to. Sorry, Kyle, okay? So, again, I would discuss the vibration is a periodic wiggle in time. Periodic wiggle in both space and time is a wave. So this was the first topic of the discussion, the difference between a vibration or oscillation on one side and a wave, okay? One of them is temporal behavior, which is vibrations or oscillations, and the other one exhibits both temporal and spatial both in space and time. Okay, light is an electromagnetic wave. This is the only thing that does not need a medium to propagate, okay, namely light. It can travel in vacuum, pure vacuum. Case in point, we can see the sun and the stars. And between us and the sun, there is nothing. Between us and the stars, there is absolutely nothing, okay? There is at some point some stuff of the star and some stuff of the air, but mainly the vast majority of the space between us in that star is pure vacuum. That's why you don't need medium for light to travel, okay? Sound, on the other hand, and any kind of medium requires, and any kind of wave, I'm sorry, requires a medium, with the exception, of course, of light. There is another wave that is kind of weird, and that wave is gravity waves. Gravity waves actually is the vibration of space itself, okay? Space and time itself. Time actually oscillates, okay? It's not fixed. So that's way beyond our scope for right now. But the point being in here, most of the waves, all of the waves actually require a medium, except light. Light, at least from the waves that we know, puzzled scientists in the beginning because the speed with which it travels required a tremendous amount of medium, and people hypothesized the existence of the so-called ether, and they were trying to calculate the velocity of the Earth with respect to ether, with the famous experiment of Mr. Michelson and his partner Morley, but at the end they did not find any speed, and Einstein came back and told them, wait a minute, Maxwell's equations did not really require any kind of medium, so why are we worried about ether? And that was something that was a big revolution in science, okay? So light requires no medium. It can travel in vacuum, pure vacuum. Again, this is the point of the discussion. For wave, it's both in space and time. I would call it a disturbance. I don't like this wiggle. It sounds like somebody is fiddling around with a little bit or something. It's disturbance, basically, whether it being small or big, okay? Disturbance, because you have a system in equilibrium. For example, when the air is calm, complete silence, okay? At that point, I have no sound whatsoever. So this is the calm air. The minute a disturbance is created in the calm air, that disturbance now starts to travel in the air. Because when the air is calm, when everything, there is absolutely nothing in it, no wind blowing, no bird whistling, no nothing at that point, the atmospheric pressure is the pressure that is where our ear is subject to. Basically, any instrument detecting sound will feel no pressure whatsoever, because the gauge pressure basically is the difference between the inside and the outside. And since the inside and the outside are sitting at the same atmospheric pressure, so it will not detect any kind of difference in the pressure. The minute disturbance is created, something falls, you speak, the bird tweets, whatever happens at that point, in addition to the atmospheric pressure, that pressure is added to the calm air, and that travels and hits the device that is receiving it, whether your ear or a receiver, and that will detect that difference in pressure. So that is basically what is happening in here. It's that disturbance that disturbs the equilibrium. Same thing with the vibration. This thing will be beautiful and sitting in its location forever and ever if it's sitting in its equilibrium. Of course, it's not complete equilibrium because I have a torsional wave now. Torsional oscillation, I should say. This thing is spinning, that's torsional spin. So if this thing is not moving, let's assume, for example, it's not moving. This is equilibrium. The minute I create a wave, I can do a torsional now, since I know this one does, or I put it as a pendulum. So in this case, all of a sudden, it's out of its equilibrium. Now it oscillates. Okay, both of them are actually disturbance from some known equilibrium. So you have a steady state, and now all of a sudden something takes it out of its steady state. So now it's going to oscillate around that equilibrium position. The word wiggle in here, I personally don't like at all. It sounds like it's kind of first of all, it's not scientific. The word that is used is disturbance. Again, uh, the period, the to and fro, the rate at which they go back and forth, which is the frequency, in this case depends only on the length, okay, and the gravity for the case of the pendulum. So if we're doing math for this frequency, the frequency will turn out to have the following units. What is it? Square root of G over L, I believe. Okay. And you have a 2 pi somewhere in here. I think it's 1 over 2 pi somewhere in here. So that is the frequency. The main thing, this is constant, this is constant, this is 9.8. It depends only on L as a square root, okay? So your grandfather's clock will need a specific L to tick the clock, to tick the second, I mean, for the period to be exactly 1 second to go back and forth, and that would be 1 second, okay? So you equate this equation to 1 over 1, which is 1, and from here you're going to determine what is it needed for the length of this clock to be exactly 1 second. It turns out the L should be about 25 centimeters. So if you're building a clock that is not this one, you probably need to adjust the time on it. There's something strange about this Zoom thing. Every Tuesday morning, I have a class with my physical science at 9 o'clock, actually 8:30. Around 9 o'clock, Zoom cuts off for briefly, okay? And it did it 4 times. It never did it with any other class. And now sometimes with your class, I noticed that it lags behind. It does not go away completely like the screen right now. It looks like it's lagging behind. So this is strange. So again, the time it takes for a full oscillation to go from 1 point to the equilibrium, to the second maximum, back to the equilibrium, and then back to where it started from, that time is so-called period. And the symbol for a period is T. Okay? So that is the time. If you take any other point, it doesn't matter. This one, for example, you're going up. So you continue up. When you're coming down, it doesn't count at this point as a full period. You have to be going back in the same direction as you started. So you need to go back to equilibrium, continue back to the other minimum, come back from the minimum to back to the equilibrium. And at this point, you have completed the full cycle. That is the time T. So you look at the clock, how many seconds that passed. This is the period. So the period is a characteristic of vibrations and also characteristic of waves. Both. Okay, okay, the mass has absolutely no effect whatsoever on the frequency or the period for the pendulum. As you saw in the expression I wrote, there is no mass. So you can put whatever mass you have in there, okay? So 1 meter long has a bob with 1 mass kilogram. No, that's the question. What is this one? Okay, suppose that the bob is now tied to a different string so that the length of the pendulum is now 2 meters. How long will the period of the pendulum change? What I wrote there for you guys was the frequency. I didn't write the period. So the period is the inverse of the frequency. And it's going to increase in this case because it's going to be increasing a square root of L, actually. It's going to increase by a factor of 1.4. Okay, waves, in their simplest case, they're these harmonics, okay? Namely, this sine wave form. So this is the harmonic that I was talking about, okay? At this point, this picture now is basically of a wave, as if you took the entire wave and you took a snapshot of it in time. So basically you have, again, like I said before, a wave is an oscillation both in time and space. So what you do in this case, you take a camera and you take a picture of the string. You will see it has this form, okay? The distance between any like points is, in any consecutive like point, is what we call a wavelength. It's in meters, it's a length actually. So the distance in this case, for example, between this point and this point, or this point and this point, or for that matter, this point and that point, or this point and this point is the same thing. All of them are wavelength. They have to be like points though, consecutively. So usually the symbol for wavelength in all the literature is the Greek letter lambda, okay? So this is the wavelength. Then it's measured in meters. This is the amplitude. Remember when I was talking about the vibration of the pendulum? How far does it move out of equilibrium? The maximum it moves is the amplitude. In this case, the maximum this wave would reach is this point. From equilibrium, that is the amplitude of the wave. Again, the crests and troughs are just basically a description of the wave, the high and the low points. Two consecutive ones, they are not a full wave. Two consecutive crests they are separated by wavelength. Two separate troughs are separated by full wavelength. Crest and the trough, they are separated by actually half wavelength, okay? So we talked about the amplitudes and these concepts in here. Again, the frequency is just the inverse of the period. F is equal to 1 over T, and it's measured in hertz. And what it tells you is how many oscillations happen, or how many waves happen in 1 second, okay? So it's a number really per second. That's why in some literature they don't use F for frequency, but they use the letter N, or actually the Greek letter mu, okay? So that's basically also another way of, it looks like a V, but it's the letter mu, because it's a number, the number of oscillations per second. So this is the relationship I was telling you. The period is the inverse of the frequency, or the frequency is the inverse of the period, okay? A sound wave has a frequency of 500 hertz. What is the period of the oscillations of the air molecule due to the sound? So there is an air molecule sitting in here. That air molecule, when sound hits it, it's going to go back and forth with it, okay? So how fast does it go back and forth, basically, from its equilibrium back to its equilibrium, for example, in the same state? So in this case, what I do, I take 1 over 500, and the correct answer, 1 over 500, is 2,000th of a second. So you have to have a super fast watch to watch it, okay? Your watch may not capture it. Before you even blink your eye, the molecule has gone back and forth. This is a 500 hertz, which is a typical sound that we hear, I guess. This is not something, I mean, it's a low frequency sound. It sounds like this, oh, okay? But a normal sound is several times higher than this. But again, that means that actually the air molecule, before you even blink your eye, has already moved back and forth, okay? That's what that means. In 1 second, it went back and forth 500 times. That's what it means, okay? For a frequency of 1,000, this thing would have gone back and forth 1,000 times. So its period in this case is 1,000th, 0.001, okay? So if the frequency of a particular wave is 20 hertz, this is one of very, very basically low frequency things that we ever are going to hear. I mean, it's one of the lowest frequencies we're going to hear, if it's sound, of course, okay? That means it does 20 times in 1 second, goes back and forth. In 1 second, 20 times, okay? So in this case, how long does it take for one of them to go back and forth? It's 1/20th, okay? So 1 over 20. Does this make sense to you guys? Okay. Simple algebra. I hope that you guys are following. Waves now, the matter doesn't travel. Actually, for example, I just was talking to you earlier that, for example, when I was talking, I did not travel from my place in here all the way to where you're sitting and basically put my mouth in your ear so that you hear me. So nothing travels, not even the air. As a matter of fact, the air where I am seated and the air where you're seated are completely different. So the air actually doesn't travel. It goes back and forth like the molecule I was describing. But what travels in this case is actually the energy, the disturbance, okay, which carries with it an amount of energy. So that is actually what travels between point to point to point to point. For this case, what travels is the energy going from my mouth up to the speaker, up to the microphone. From that point on, it's completely different electronics. In other words, you can change the intensity. You can lower it down, or you can increase it depending on the gains in your device, in your speakers. And from there, you're going to have a different intensity than the one that I have produced. But the point being in here is what travels from here up to the speaker, up to the microphone is actually the energy, okay? What travels from your speakers to your ears is actually also the energy. And this is true also for light. This is true for any kind of wave, as a matter of fact, okay? So for example, I'm going to have this medium. You see, the disturbance I create on this side, on my right side, probably looking at the left, is traveling and goes all the way back and forth and actually produces a sound too, okay? And it stays, but this is an attenuated wave because of friction and air resistance and energy lost to the medium and all of that. At some point, the vibration will stop. If there is no attenuation, if there is no friction or anything like that, this thing should go forever and ever, okay? And this is a case from what looks like actually standing wave. I don't know if you see it or not for a moment. There is a big node in here and big node on the other side, because on the other side actually is also fixed too. So the minute it hits the other side, it actually bounces back. So this is basically an example of a standing wave too. Did somebody say something? No? Okay. So in this case also, to create a disturbance on the surface of the water, it's going to travel, and you're going to see actually nice circular waves that travel toward the surface in this case. This is an example again of surface waves on the water. They have definitely a speed. Some waves travel faster than others, okay? So that is something that is also characteristic of waves, okay? The speed of a wave, in this case, a wave with wavelength 10 meters and time crest is 0.5 centimeters, then it's traveling by 10 divided by 0.5. The formula for the speed then, because is actually usually the speed is the distance divided by time, and the only distance we have at this point we discussed is the wavelength, okay? And the only time we discussed is the period. So this is actually the formula for the speed, okay? This is called the dispersion law, okay? This is just for a specific kind of waves which are called the harmonic waves. They look like this. They look like sine waves, okay? If the wave is a little bit different, so you need to have a little bit, this formula will be altered a little bit. But assume it true, okay? For sound, for example, it's the speed of sound is the wavelength of sound divided by the period of sound, or the wavelength times the frequency too. That is another way of doing. You never hear somebody giving you the period of sound. They always give you the frequency. If you're curious trying to find what the period was, you just divide, invert it, and that's it. So these formulas are the same. Okay, the velocity is lambda, which is the wavelength, times the period, times the frequency, I'm sorry. So this is the rationale for that calculation. Again, I was giving the example of the slinky. The slinky exhibits this compressional waves or longitudinal waves, and also it can exhibit transverse waves. So I'm creating a wave transversely. Now it goes back and forth. So a slinky is a good example. Obviously, if I can create a wave in here, actually I should have created it this way. Let me stop this first. I have a standing wave, actually. I found a standing wave in here. Or, let's see. This is actually, I'm creating also compressional waves. This is actually a complicated wave now because it's doing both. A combined wave, I should say, not complicated. Again, transverse wave, we defined what they are. Radio waves, light waves, S waves for the seismic waves. They are all examples of strings, also all examples of a transverse wave. Okay. So again, we're talking about the distance. So this question is immediately about wavelengths. I'm looking at the clock now. All of this discussion should hold true for the sound. Actually, all along I was giving examples with sound too. So nothing is different in here. There will be probably a couple of things in terms of these things that are. So again, the wavelength is valid for both of them. The vibration along a transverse wave move in a direction perpendicular. That is by definition. Longitudinal waves or compressional waves, the one that I was showing earlier in the slinky, is the distance of the disturbance, which is in this case along the slinky itself, and the wave travel in the same direction. Okay, travel in the same direction. Okay, these are called compressional waves or longitudinal waves. They have the same name. Okay. In the case of sound, we have two things going on. What your mouth does, actually, it creates a pressure. That pressure basically compresses the air between it. So when the air compresses, it leaves a void behind it. That void is called the rarefication. So what happened in this case, you have the succession of compression followed by rarefication, compression, rarefication, compression, rarefication, traveling. The distance between compression and the compression and between them is the rarefication is the wavelength. Okay, how often this changes? That is the frequency. So it's similar to sound waves, liquid waves inside the liquid actually, and gas in general because of the volume behavior, and the P wave in the seismic waves also. There are all types of examples of the longitudinal waves or compressional waves. So this is what I was talking about in here. This is a compression, rarefication, and so on and so forth. And if we have a tube in here, I don't have one, we have a lot of them in the lab, you can actually put a tuning fork in here and the sound will appear on the other side, basically, as amplified, as a matter of fact, from this thing in here. This is the P wave, so. Again, the wavelength of a longitudinal wave is the distance between successive compressions or successive rarefications. Both of them are true. So this distance from here to here is actually wavelength, or from here to here is actually wavelength, same thing. As long as you have between them, between these two compressions, you have rarefications, you're in good shape. Interference of waves, again, is when two waves combine. You can have two kinds of interference. Let me stop sharing that screen in here quickly and show you with from the other screen. Where is the share? Oh, come on. So I have two waves, one traveling to the left, or to the right in this case. So this is a right wave. And one is traveling to the left. Okay, I have a left wave and a right wave. They continue traveling, let's assume with velocity v1, the same velocity, okay? Doesn't matter the velocity. The point being in here is when they meet, this is what happened. Let's say, for example, this is a string, it's calm until it's hit by this disturbance, then it goes out of equilibrium, okay? where they meet, they're going to meet somewhere in the middle, somewhere in here, for example. So this is how the string would look like when they meet. Okay. So at this point, the two waves will amplify one another, and there it's just the sum. So this is basically the sum of the two waves. So they added in this case, they become much more stronger. After they leave, after the collision, after they collide, the one that was to the right will continue its path to the right. So this one will continue actually going this way. There's no problem with it. And it's the same wave as it started with. The one that was going to the left will continue also its path to the left. There is no problem with it too. So this one will be probably here and will continue in its path. So they emerge from the collision as if nothing happened. But during the collision, they will amplify one another. This is called constructive interference. In other words, they add up. Let's take another scenario in here where I have two waves again, one traveling to the right. So this is a right wave, and another disturbance traveling to the left, okay? I'm assuming that they have the same intensity. Again, I expect them to meet somewhere in the middle. When they meet in the middle, this is how the link, if they have the same intensity, this is how a string would look like. They're gone, they disappear momentarily, okay? This is a signature of what we call interference in this case. Now, when they emerge from this collision, again, the one traveling to the right will continue to its path. So when it emerges, going to emerge this one and continue to the right. The one traveling to the left will continue also traveling to the left, and this is more or less how it's going to look like. Okay. So this is actually a different kind of interference, and it's called the destructive interference. So this is the two kinds of interference, destructive interference and constructive interference, is again unique to waves. And you can see it on the surface of water. If you put, for example, if you send two disturbances, where they meet, you can see them canceling. There is unique interference patterns that form because of this. Okay, where they meet, there will be always cancellations with their the max, the crest, and the trough meet. And where the crest and crest meet, or the trough and trough meet, you will have a high intensity. In this case, it's going to be higher, more visible. So again, this is what I was talking in here. So there is a reinforcement in the first case, so the intensity is twice, and there is cancellation in the case of destructive interference. This is again on the surface of water. You can see clearly where they cancel, okay, and the maxima will be intensified. When you see this, you know you're dealing with waves. This is a signature of a wave. So that's the second point in here. What is the signature of the wave? What do waves do that nothing else does? They interfere with one another. When I say interfere, I mean this way, not the one that they do in American football. That is not meant with it. It's still not interference. I mean, that's just brushed his hand. You can clearly see the two hands basically before and after and during. This one, they disappear, okay? So not the one that is meant in American football. So this is the unique signature of waves. So what is unique about waves? They interfere. Standing wave is an example of interference. In this case, you create a wave. It's going to be reflected. Once it reflects, it's going to be inverted. So the one that is coming back is going to come back on the opposite side. And if you keep on moving it up and down, you're going to create a unique pattern in this case, and the pattern will be characterized by nodes that form. I have one node in here, I have another node in here, and I have a third node in here, and I have an empty node in here, and an empty node in here. So I have, in this example, 3 nodes, and between the 3 nodes, there are 2 empty nodes. Always the number of empty nodes is just one number less than nodes. Okay, I have created, actually, we can create as many patterns as we want. So this is just one excitation with 2 empty nodes. You can have more than 2 empty nodes. Okay, this is the definition of nodes and empty nodes. For example, in this case, the first one we have only one antinode. In this case, we have two antinodes. And in this case, actually, we have three antinodes. If I count how many nodes there are two in here because it's always plus one. There are three antinodes. There are three nodes in this case because I have 1, 2, and 3 because I have two antinodes. And because I have three antinodes in here, I must have four nodes. I have 1, 2, 3, and 4. Okay. So this is not, you don't need to stop in here. You can have 4 antinodes, you can have 5 antinodes, you can have as many as you can. But this is unique to the case where both ends are fixed. Okay. In a string where it's not fixed, for example, if you whip the string, the lowest number of nodes that you can have actually is one node, and in here it's going to be in one antinode. So this case is just unique for when both ends are fixed. But in here, when the end is free, when one end is free, you can have exactly the same number of nodes and antinodes. Okay. For example, you can form this. So you will have one antinode, two antinodes. I mean, two nodes, I'm sorry, one node and one node, that's two nodes. One antinode and one antinode, that is two, okay? So in a free end scenario, you can have both the number of nodes and antinodes is the same. And this, of course, leads to musical instruments because they're all based on standing waves, actually. And the beauty that you hear or what you think is pleasant is due to the fact that you're hearing this repeating patterns forming a pleasant sound in your ears. So that's basically how that is. And like normal sound discussions, conversations, they don't have that regularity and rhythm in them. Again, the Doppler effect has two things in it. Let me stop sharing this thing in here to talk about the Doppler effect quickly. Sometimes it does that. I have to get out and in and out, okay? So the Doppler effect, what I have in this case, oh, I'm sorry, I'm not even sharing my screen, I'm sorry. So you didn't see the problem I ran into. Good. Okay, so what we have in this case, we have three things. We have an observer. We have a wave. Okay, and we have a source. So the source can move with its own velocity of the source. The wave can have its own velocity, and the observer can also move too. So everybody can move. So let's take this picture in here and try to think about it. If my source is here, for example, and it's moving this way, and as it's moving, it's sending waves, for example, sound waves, okay? If it's not moving, they appear to be separated by their wavelength. So if the observer is sitting in here and not moving, the observer is stationary, then, and if the source is not actually moving, then the observer will hear the sound coming at specific intervals. That is the wavelength, okay? But if the source now moves, it sends a wavefront and then follows it. So it sends one and then follows it. As the other one tried to reach this point, so it would have been separated by this distance. No, the source moves to this point. So actually the separation is shorter, appears to be less than the other ones. So you're going to hear less and less, in this case, distance between wavelength. And as I said before, your ear perceives waves with this velocity, which is the velocity of the wave, which is the wavelength times the frequency. Since the wavelength appears to be shorter, you're going to hear higher frequency because your ear thinks the sound travels with the same speed, and always sounds travel with the same speed. It doesn't matter. So the observer thinks that the frequency is higher and higher, although it's the same frequency. So if the source is stationary, he will hear a specific pitch. But if the starts to move towards him, then the pitch will be higher and higher because of the fact that the wavelength is shorter and shorter. It appears to be shorter as it sends one wave. So let's say, for example, it was 10 centimeters. Now it's probably 8 centimeters instead. So it appears to have shifted toward lower frequency, lower wavelengths meaning that the frequency will be higher because you divide by a smaller number. Now, if the source is not moving, but the observer is doing the other way around now, is moving toward the source, it's the same thing. He's covering now this distance, and he's anticipating when the waves are going to appear. So again, he's going to hear higher and higher pitches. Now, if the observer is on the other side though, okay, and the source emits a sound wave here, and the wave is supposed to be reaching this point. So by the time it reaches this point, that is a period, it's going to emit the next wave front. The distance is actually longer. It's probably about 12 centimeters. So if this lambda is longer, the frequency is going to be less. You divide by a higher number, so it's going to be less. So he's going to see the frequency going down as the source is moving away from him. Now, if the source is stationary and he's moving away, it's the same thing. The distance appears longer and longer. So in this case, the pitch will look like it's getting into lower and lower frequencies. Okay. So this is basically, in a nutshell, what the Doppler effect is. In general, though, it could be all. The source could be moving, and the observer could be moving, and of course, the wave is moving. So now what you're talking about is the relative motion. The relative motion is the one that dictates whether the frequency will increase or decrease. So for example, if you're driving, and let's say, for example, police officer is behind you trying to go somewhere or trying to come after you, actually, okay, hopefully not, then you don't have to turn around. You could tell if he's gaining distance over you by just listening to the sound. If the frequency is going higher and higher pitches, you better stop because you're gaining ground on you. If it's going less and less in this case, then you're actually gaining speed on the you have to be safe in this case, okay? Now, if there is no change, and if you notice that you're doing 65 miles per hour, he's also probably doing 65 miles per hour, okay? So that is the point in this case. So that is how you see about it, you look at it. So this is in a nutshell, and you all experience the Doppler effect somewhat. Even if you are sitting still and the siren, for example, of an emergency vehicle, for example, the fire department or an ambulance passes by, you experience this phenomenon. So that's, you know what it is. Now, this is true for all waves. It's not just for sound. And I'm talking in terms of sound, but it's true for all waves, regardless of what the wave is. They all exhibit this behavior, including light, by the way. And this is how we discovered that the universe is expanding, actually. When Mr. Hubble looked at the specific stars, for example, in Andromeda Galaxy, which is our big neighbor, he noticed that those stars, their frequencies are supposed to be in specific points, a specific location, but they are shifted. No, actually, I'm sorry, not that galaxy. Galaxy, no, that is a bad example. Actually, he used that, but it's not for that purpose. But for the further away stars, galaxies, he was able to determine that actually they were shifting toward the red. The frequency is shifting toward the red. In other words, shifting toward longer wavelengths, because red is longer wavelength than the blue. So the red shift in this case indicates that the galaxies, as they are further and further away from us, they are moving faster and faster away from us. Hence, the universe is expanding. So that's really how the result is. This study of the Doppler effect cannot really, for the universe, cannot be used for the nearby galaxies, although Andromeda is about 2.5 million years away from us in here, which is kind of a neighbor, between 2 to probably 3, but it's still very close, I mean, relatively speaking. I mean, it takes for light 2.5 million years before it reaches us, but that's something else. As a matter of fact, there are newer studies that indicate that both our galaxy and Andromeda are actually colliding as we speak, okay? Anyway, so this is the blue shift. If light shifts toward the blue, that means the thing is coming towards you. If it shifts toward the red, that means it's moving away from you. An example for it, for example, if you have a star, okay, let's say, for example, it's orbiting a black hole that we don't see. So it's orbiting something and it's going around in a circle, okay? And which is within our eyesight. This is where the sun is. So at some point, the star is moving away from us, and we can see that it's shifted toward the red. The frequency of it is shifted toward the red. Let's, for example, focus on a specific wavelength, for example, for transition, for example, for a specific element. Let's say, for example, hydrogen, and we know hydrogen, all of the frequencies that emits. This frequency is supposed to be sitting in here, but we see that it's moved toward the red. All frequencies have moved toward the red, actually. So we know that this star is moving away from us. How much shift is how fast it's moving. Now, if it's on the other side, when it comes to the other side, it's going to come towards us, okay? So in this case, we know that it's coming towards us, so the entire spectrum now moves toward the blue. So we know now it's moving, how fast it's moving, and it's coming towards us. At some point, it's not going to be moving towards us or away from us when it's doing this too. Because in this case, it's just moving sideways. In that case, I will not notice any kind of Doppler effect. So in the sense that the spectrum will be exactly what I expected, okay? It's not shifted toward the blue or the red. So this is some of the things used in astronomy, actually, and used actually by police officers to stop you too and tell you that you're moving. They use Doppler effect actually too, okay? So that is used in the industry, is used everywhere. So the Doppler effect occurs for both sound, light, and any wave, actually, as a matter of fact, that does it too, okay? But these are the two main applications that we have. So the wave barrier, when we have basically, actually this one, you can see it in the wake of boats in general. But in the case, for example, of sound, again, the source is moving with the same speed of sound. So in that case, basically, there is a buildup of waves because it emits a wave, and the wave is supposed to travel this distance, okay, before the next wave hits, because every t time, every period is going to emit another wave front. That's exactly what the period means. Every t seconds, it's going to emit another crest, if you wish, okay? But if the plane or if the object is moving with the same speed as sound, so if the wavefront is supposed to be here, when the next one hits, the next one actually will be emitted right in that point because the plane will be sitting right on that point, okay? So now you have two wavefronts sitting on one another. Of course, this one is traveling back behind the plane, and the other one travels just barely as was created. So there is a difference too. But now it moves a distance and emits the third one. And the third one would be right on top because the other ones are again trying to travel from this distance, both of them, the first one that was created and the second one that was created, they're supposed to travel this distance, lambda distance, in a given t time, which is the period. And by then, the plane also, or the object, will be in that position too. So now there are three wavefronts sitting in there, and there is a pile, there is a buildup, okay? So if the pilot is not careful enough in this case, there will be tremendous energy that will build up, and it could cause vibrations, violent vibrations, and the whole thing will collapse, okay? Instead, if you go to supersonic mode immediately, so what you do in this case, you send a wavefront, and the objects, so this is a subsonic, this is exactly at the speed of sound, for example, in taking the case of sound. If you go supersonic in this case, you send a wave, and the wavefront moves, but the plane will move beyond it when it sends the next one, and so on and so forth. So there is a cone that forms now, okay? And in that cone, there is actually a pileup. So if you're sitting in here and you're unaware of the plane because you are not paying attention, you're not looking at it, you're waiting for the sound to hear it, there is actually a big boom that you're going to actually, as you're going to hear it, you're going to pile up basically a lot of wavefronts. They will hit your ear, and you will hear the so-called sonic boom, okay? So that is, again, sitting in here. But the plane will have way gone at that point, okay? In this example, they use a bug. I don't know why they do that, okay? So those are the so-called shock waves, and they form in this conic shape in here. They travel in space, so that is exactly the plane in here. Did any one of you experience the this thing, shock wave from planes? Did anybody attend one of those military exhibitions where they do that? No, I don't think that they do them supersonically. Did they? Do they? I doubt that they do that. Yeah, sometimes they pass by and you don't notice it until you're hit by a huge sound. And then you look up and the plane is way back. It's gone already. Okay. So again, this is the shock waves, and that is the sonic boom I was talking about in here. These are the two observers, and the plane is already passed before this one will hear it. Okay. Observers see already has passed by him. Okay, sound I already talked. Let me see exactly what we need to cover other than what I already covered. Okay, it has to do with two things, either the pressure in the atmosphere. I mean, we're going to talk about the intensity of sound. How much time we still have? We still have time, actually. Let's finish this quickly here. So again, the intensity is measured actually in decibels, and it has to do with the pressure that we hear. The human ear is sensitive to pressures of the order of 10 to the negative 12 watts per square meter. Super weak, basically, sound in terms of intensity. And that is the whisper, okay, or even less than that. But it can tolerate up to 1 watt per meter square. 1 watt per meter square. That's a lot of sound. If you go to a place where, for example, near a takeoff where the airplane is, that is tremendous sound pressure. Okay, but it's still 1 watt per meter squared. So it's really a tremendous pressure, but it's not as much as the, for example, other sounds too. Now you have to be very careful because those yanking in and out of your eardrum can cause rupture in it. So you have people who work in, what is it, that kind of music that uses super loud stuff. You have to be very careful with it. So that is one characteristic. Instead of using this pressure, we use a decibel actually, and the decibel is the log of the powers of 10. So the decibel in this case ranges from the order of 0, because the natural log of 1 is 0, up to log of basically in the base of 10 to the pressure divided by the maximum pressure divided by the nominal pressure. And the nominal pressure is 10 to the negative 12. So it's going to be 12. I mean, 12 times 10, because they have to multiply by a factor of 10. So it's 120 decibels. Anywhere between 0, I mean, a normal conversation like right now, for example, we're having is about 60 or 70 decibels probably, okay? A louder conversation can reach 90, 100 decibels. That's too loud, okay? 60 decibels is kind of soft. 40 decibels is super soft, okay? 0 decibel is basically the threshold of hearing. That is when you start basically barely you can hear anything, okay? At least with the human ear. Some animals may detect those lower intensities, but that's basically how we humans, our ear has evolved. Now, 130, 140 decibels, probably we can tolerate them. That is the onset of pain. At that point, you will feel pain in your ear, okay? If you are exposed too long for it, that is going to be damaging to your ear. So that is basically in terms of the intensity. In terms of the frequency, we hear anywhere between, I think, like, 20 hertz, all the way to about 20,000 hertz. And that depends, again, on the age of the person. Some people who are, I mean, when you grow older too, your frequency will drop down. You're not going to be hearing frequencies of the order of 20,000 hertz and so on and so forth. That's why in some communities, what they do, for example, with those kids basically producing a lot of noise and playing the street with their skateboards and so on and so forth. So what they do, they emit super loud, annoying noises at super high frequencies. Obviously, the people they cater to who are usually of an older generation, they don't hear that. They are walking as if nothing is going on. But the kids, they're so much annoyed, they don't stay there because it's too much noise and too much sound. So again, they are taking advantage of this thing in here. And I think there's some community who did it, and I don't know what happened afterwards. Okay, again, so this is something that also changes with age. Now, other animals, like for example, dogs and bats, they hear for very high frequencies, much higher than we do. And they can pick up sounds with different frequency that we don't even know exist. And some other animals on the other side of the scale, for example, elephants and whales, they hear even lower frequencies than what we hear, and they can communicate, and they could have very long conversation, and we would not even be aware that it exists unless we have instruments in there to check those low frequencies. Then we will see that things are happening on, and we were not aware of it. So those are the two key things in terms of sound. in terms of everything else, interference, in terms of the reflection, as I was talking about in here, where the wave is inverted. All of them, they're identical. They're between all waves exhibit those things, okay? But the thing that is unique to sound is the fact that it's a compressional wave. And of course, it can be converted to an electronic signal. That's exactly what we're doing right now, okay? Through capacitors, actually, device that we will learn later on in electricity, okay? The speed of sound is around 343 in room temperature right now. That is how fast sound moves. At 0 degrees, it's 330. So it increases with temperature. It changes with temperature, okay? So that's the one of the things. That's the velocity of sound. So for example, I was doing this is 512 hertz. This is 512 hertz, and I have 343 for the speed. 343 divided by 512. I can find how many centimeters the wavelength was, or actually, it was about half a meter. Is it 330 divided by 512 is roughly about 67 centimeters, the one that this produced, and you guys picked it up, okay? The wavelength. In other words, between crust and crust, the one that you heard was about this distance. That's about 60 centimeters, okay? Maybe slightly more, 60 centimeters, okay? So that is the wavelength that this produced earlier when we did the demo, okay? Because again, we have the speed 340, because we are at room temperature, we're not sitting at 0 degree Celsius, and 340 divided by 512 is roughly about 60 centimeters, okay? Something. We're closing to. Again, the law of reflection that we discussed in the lab is the angle of incidence must be equal to the. So let me talk about Snell's laws, and then we'll call it quits, because everything else we talked about. So let me talk about Snell's laws, and then we call it chapters. Hold on. Let me share with you this screen. Again, for those sitting in physics 11, we discussed this in class, so you guys are good. So the law of reflection. I have an incoming wave. I have a medium in here that is reflecting waves. I'm going to take the example of light. This is the normal to the world, to the medium. So this is the perpendicular to it. So if I send a wave, this is the incoming wave, or the incoming signal. It makes an angle of theta incidence, in this case called theta I. This is the angle of incidence. It's made with the normal. The law of reflection states that the reflected wave in this case makes an angle theta r reflection that is by law equals to the angle of incidence. This is how the image forms on the in front of the screen. When you are standing in front of the mirror acts as a reflector in this case. So you're standing in front of the mirror and you're here, okay? And you look at every object in the, I mean, you have a long hand, I'm sorry. So you look at your feet, for example, and the ray that is leaving your feet and coming to your eye follows this law. The angle of incidence, which is this one, this is theta I, must be equal to the angle of reflection, theta r. And for you, it looks like as if this image actually, this ray is coming from here. So you form an image in here for your foot. Now, if you look at your hand in this case, your hand is actually following the same Snell's law. That is, the angle of incidence is equal to the angle of reflection. For you, you form an image that the hand is coming from there, and you replicate yourself on the mirror. So this is how the image forms on mirrors, whether it's a flat mirror, like in this case, which is a reflective mirror, or a concave mirror, or a convex mirror, okay? The only thing different is, in this case, the flat mirror will have a perfect replica of you. In other words, there is a one-to-one correspondence. This distance is the same as this distance, and the ratio of the height is the same. So the magnification actually is equal to 1 in this case. Actually, it's equal to +1, yes, okay? In this case, the magnification may be more or less depending on where the object is. As a matter of fact, the image can be inverted or not inverted. So in this case, there's all kinds of stuff going on in the case of the image. Okay, for your retina, for your eye, okay, for your eye, so that you guys know what's going on. you have a lens in front of your eye immediately. So the whole scenery that comes from outside is actually inverted in the lens, and it's backward, okay? So if you're looking at me and you think that I am standing like this, if somebody looks at your retina, I am like this. Everything is backward actually for you. Your brain adjusts the image backward and puts it now to look like everything is normal. That's why when you walk, you don't bump into things thinking that they are up, but they are down. So everything is fine and you walk as if nothing happened, okay? So that is how the image is formed on the retina. The retina itself behind the eye is actually inverted, okay? And it's actually smaller than what it is. So the brain fixes all the things for you and you're fine and you can walk fine, okay? So this is based on the law of actually the case of the lens that is in your eye, and even the lens that is in the glass in this case that I'm using is actually uses another law, and the law that uses is actually the law of refraction, okay? So I have the difference in media in the case the material of the lens is kind of very thick and it looks like it's glass. I have separation in this case, so this is the equivalent of glass if you wish, or water, okay? And this is air, for example. And the angle of incidence is like this again too. So you have a wave that is coming in here. We still have a few minutes and we're going to close. So this is the refracted in this case. So this is theta r. R stands for refraction in this case. And this is incidence, theta I. Again, the index of refraction for air is 1, or it can be any material for that matter. And the index of refraction for water is N for water. This is exactly the same index of refraction, more or less the one that is in your eye, okay? It's 1.33 or something like that, I think. So the law of refraction states that the signs follow this relationship. N1, which is this medium, times sine of the angle of incidence is equal to N2, which is this one, times the sine of the angle of refraction. So these are the laws of refraction. And again, they're also necessary for the image formations, okay? To understand how images form. And if you're playing at all with your camera and you're trying to zoom on an object, okay? And you change either the focal length, because all mirrors have a focal length, all optical instruments have focal lengths, including, by the way, the flat mirror. It has an infinite focal length, basically. The concave and the convex, they have a specific, depending on their convexity or their concavity, they have specific focal points where all the rays focus in it. So that's what you do actually with the camera too. So you change, in this case, you don't change the distance to the object, basically where the film forms, or where the what is it, the CCD of the camera is located, where the image actually forms in the background. That's fixed. So what you do in this case, you change your lens to move it back and forth to have a better focus, or actually you move backward, okay? Like for example, for a phone, if the object is out of focus, to bring it into focus. Again, this is sometimes also used for corrective lenses too. If a person, for example, the image doesn't form on the retina and fall behind it, they use corrective lenses to bring the image from the behind the retina to the retina itself. Or the other way around, sometimes the image actually forms before, when you have a long eye, it forms before the retina. So in this case, they use corrective lenses to move the image back to the retina so that you still can see with it. So again, there's a lot of nice stuff in here that is involved with the laws of reflection. Anyway, everything that we discussed up to this point is the entire 2 chapters. So I rely on you guys to finish the stuff, which is really, all of it is discussed somehow in here. And I will see you guys on, today is Tuesday, so I'm going to see you on Thursday to continue this discussion. I promised you a musical number, so I'm going to do that on that day, okay? And I'm going to decide on that day whether or not, and you're going to help me whether or not really I should quit this job and go into music or not. Okay? You guys going to be there to watch me perform? Okay, so I'm going to rely on your critique in there, and hopefully I will make it to become a famous musician too. Okay, let me stop the recording.